Hello, everybody. I'm Paul Beckwith, and there's always loads of things for me to talk about, climate events and catastrophes that are occurring around the planet. So this is the first video. I'm going to do a video session, filming session, and, release, tell you about a couple of the topics that I'm going to release shortly. So this particular video is a follow-up to the previous video that I made on the Intergovernmental Panel on Climate Change, the IPCC Assessment Report 6, AR6, the synthesis report. Now, on the IPCC website, they had a summary of the report, which is about 36 pages or something, and I covered that in a video. But just yesterday, I believe, they released a longer version. I think it's about 86 pages or something report, and there's extra figures and stuff in there. So this is what I'm going to cover in this video now, and I think there's supposed to be a final full report, much longer. So when that comes out, I'll do a video on that also. But I'll try to focus on the, what's new. I'll refer you to my previous video on the AR6 Synthesis Report, Climate Change 2023. And I also want to talk about a paper. I'll do another video, separate video on the Arctic sea ice, because I haven't given an update on that. Specifically, I'll be focusing on where we can expect the last remnants of ice to be in the summer, just before it vanishes and the Arctic Ocean is completely open in the summer. Or at least the end of the melt season, September, in the near future. And most scientists think it'll be the last vestiges of ice will be fast ice around the land. But those latitudes are quite a bit lower than the North Pole. So I was saying, well, maybe I think it'll be circling around the North Pole when we have this, just before we have this blue ocean event. So there's a paper that actually talks quite a bit about, it argues that the thickest ice being in the Lincoln Sea, that's the area maybe where there will be the last vestiges of ice. That's just north of Greenland. It's sort of the bay between Ellesmere Island in Canada, northern Canada, and Greenland. It's around the Nares Strait, which used to have an ice bridge which would stop the thickest ice from going down and escaping the Arctic through the Nares Strait. But of course, the ice bridge doesn't form, or it gets broken up very, very early. So that's not the case anymore. So I'll talk about that. And I also need to do a quick video on this terrible tornado. There were superstorms that went through the southern U.S., and tornadoes spun off, and a massive tornado, killed at least several dozen people in Mississippi. And I'll show you I followed this on radar actually last night as it was occurring. Massive tornado, one of many that hit the state. But it looks like a war zone. Everything's kind of disintegrated in this town, in a couple towns there. So I'll do a separate video, a third video on that, and they'll be coming. Maybe I'll release them all back to back when I finish filming today. I'm on a roll, so when you're on a roll, keep rolling, right? Okay, so let's go over here, swing my camera around in my messy office, and which one day I'll clean, and I'll be sure to show you on video what it looks like. So if you just Google AR6 Synthesis Report, IPCC, you can find this page. It's ipcc.ch/report/AR6/SYR/. And there's a whole bunch of sections here. So I talked about the summary for policymakers in a previous video. The longer report's being released, the full volume. I'm interested to see how many pages that will be. So I've talked about the figures that were in summary for policymakers and so on, and the presentation, press releases, etc. So anyway, this is how you find the report. So I'm talking about the longer report here. So if you click on that, you can get the report. It's 85 pages long. And I like what they say here, longer report. Yes, of course, it's a longer report. So Again, I'm going to focus mostly on the figures, but let's have a look at the let's have a look at some of the key findings here. And they put the key findings in. So just by way of intro, so I'm going to go over, I'll try to cover the main points in the figures. So this synthesis report of the IPCC 6 assessment report, so it summarizes the state of knowledge of climate change, its widespread impacts and risks, climate change mitigation and adaptation. So it's based on the peer-reviewed scientific, technical, and socio-economic literature since the publication of AR5, the 5th assessment report in 2014. Okay, so it integrates the main findings of the AR6 working group reports, okay, and the 3 AR6 special reports. Okay, so it tries to integrate all of this stuff, yeah, so those are some of the key things. So those are some of the key things. So let's kind of focus, as we go through here, I'll focus on the figures that I can see. So this page here, yeah, so human activities through the emissions of greenhouse gases primarily, we've unequivocally caused global warming, with global surface temperature reaching 1.1 Celsius above the 1850 to 1900 average, the climatology, if you like. This is the baseline. And it's compared to the decade from 2011 to 2020. So if you look at 2023, 2022, I mean, we're 1.2, maybe approaching 1.3 Celsius, but closer to 1.2, I believe, above this baseline. And if you compare this baseline to the original pre-industrial date of 1750, you need to add 0.2 or 0.3 degrees to that. That was when the IPCC and the COP meeting started talking about 1.5 and 2 degrees, the original reference was to 1750. So you need to add 0.2 or 0.3 to this number. If you take the 1.2 number in 2022 and add 0.2 or 0.3, you get 1.4, 1.5, which is, we're already almost there. I think the next super El Nino, if this El Nino coming up is a super El Nino, we're going to blow apart the 1.5 and be well on our way to 2 degrees. The global greenhouse gas emissions are still rising, and they're rising at ever faster rates. There's also unsustainable energy use, and land use change, lifestyles, patterns of consumption and production across regions, between and within countries, and between individuals. We're still on this runaway train, and I think we went off the cliff and we're in the air right now. So we need to claw our way back to the cliff if at all possible. Human-caused climate change is affecting many weather and climate extremes in every region across the globe. There's widespread adverse effects on food and water security. The UN just had a water conference in New York this past week. Human health is suffering, both physically and mentally and emotionally. Economies and society are getting hammered. Lots of money is being spent to rebuild things, and if we rebuild things in areas like coastal regions that were flooded, I mean, that's just like idiotic, right? Related losses and damages to nature and people. The last COP, the COP 27 in Sharm el-Sheikh, Egypt, was focused on loss and damage mechanisms. Vulnerable communities who have historically contributed the least to current climate change are disproportionately affected. Okay, so this is open source. I highly recommend that you read it, that you have a look through it at the details. The increases in well-mixed greenhouse gas concentration since about 1750 are unequivocally caused by GHG emissions from human activities. This is a fact. Land and ocean sinks have taken up a near constant proportion. About 56% of the CO2 per year over the past 6 decades, with regional differences, so it's only the 44% that's going into the atmosphere that's causing the rise of concentrations in the atmosphere. And we're reaching unprecedented levels. CO2 concentrations, current CO2 concentrations are higher than at any time over the past 2 million years. Since 1750, CO2 has increased almost 50%, methane's gone up almost 160%, nitrous oxide 23%, right? Huge amount. So let's look at the figures here. So human activities are responsible for global warming, and here's the global surface temperature map since 1850 up to the present day. There's also a color-coded scheme here. Red is getting hotter and hotter. This is the warmest multi-century period in more than 100,000 years, and you can see that we've reached, over, in 2020, the number looks like here, it's almost 1.25, it looks like to me. The observed warming is driven by emissions from human activities, with the greenhouse gas warming is partly masked by aerosol cooling. So if you look at the observed warming, we're here. This is, this is 1.1 degrees because they take it from the baseline to be 1850 to 1900, and the 2011 to 2020. They said what is that right? 2011 to 2020. Okay, so they take the average that decade, and that's how you get the 1.1 here. So the total human influence, the total human influence is causing the warming, the whole thing. Well-mixed greenhouse gases would bring the warming up to 1.5, but there's some cooling. Okay, there's aerosol cooling. Other human drivers, we put so much aerosols in the atmosphere, they're hiding, they're masking about 0.4 degrees of the warming. Now, people sometimes say, well, the sun's changing or volcanoes are having an effect. Well, this is the error bars, right? Maybe plus or minus 0.1 effect. The internal variability, this is from El Nino, plus or minus about 0.2 degrees Celsius effect. Okay, so it's the greenhouse gases that are causing the warming, and they're offset by some aerosol cooling. So if we suddenly stopped all that aerosol cooling, we would immediately jump up to 1.5. Okay, these are how the concentrations of greenhouse gases have increased since 1850. So CO2 up to, and this was in 2019, we're over 420 now, parts per million, CO2. Methane increased, slowed down around 2000, upticked around 2007. We're over 1900 parts per billion now. I mean, this was a few years ago. And nitrous oxide, 332 parts per billion. So the global warming potential of methane is, if you take a 100-year time scale, it's about 34 times that of CO2, molecule per molecule. And over 20 years, it's more like 86 times. And over a few years, it's more like 150 to 200 times. So very, very huge greenhouse gas effect, even though it's at the part per billion level. Nitrous oxide, also very, very high global warming potential. I think it's something like 300 or something. And here's greenhouse gas emissions from human activities, how it's broken down. This is CO2 from fossil fuels and industry, burning carbon, producing CO2, whether the carbon's in the coal, in the oil, in natural gas. Then there's CO2 from land use change, and forestry. So we've got this LULUCF. Okay, if you see this acronym, that's land use change, and forestry. And so we've got rid of some of the sinks, and so the land isn't capturing as much CO2. So this is a human effect, which has driven it up. And then non-CO2 emissions. This is these, so not CO2. So this is the methane, the CH4, it's the nitrous oxide, halocarbons, etc., which is bringing it up. So this gives you a greenhouse gas emissions, gigatons of CO2 equivalent. So So equivalent, and this is per year, so we're pushing up to close to 60 gigatons of CO2 equivalent per year. The actual amount from the CO2 itself is, total is about, something like close 42 or something. Okay, just from burning is, lower. It's about, I'd say, it's about 40 or so. Okay, so you add all these together, and this is causing our problem. So let's go to the next figure here. Emissions have grown in most regions, but are distributed evenly, both in the present day and cumulatively since 1850. Grown in most regions, and then of course they spread out around the planet. So this is historical cumulative net anthropogenic CO2 emissions per region. So you can see so North America. I'm just having a look here. This is net CO2 from land. This is the CO2 from LULUCF. Okay, land use change. Right, that's the gray part. And this is fossil fuel and industrial emissions, FFI, if you like. And then, so those are shown here, and they're also used in this plot here. That's the scale. So basically, this is cumulative emissions since 1850 to now. So basically, North America is 23%. Okay, and this is gigatons of CO2 equivalent, I guess. No, it's just CO2 emissions. Okay, so 23% North America, Europe 16%, Eastern Asia 12%, Latin America and the Caribbean 11%, and so on. Notice international shipping and aviation is often left out. That's 2% here. Okay, so the bulk of it, this is cumulative. Of course, Europe was developed much earlier, the earliest, and then North America, when it was developed, it kind of took over the emissions. Other countries are catching up, other regions are catching up, but this is cumulative. So North America is still in the lead by far, followed by Europe. Asia only comes in third place, Eastern Asia, and Central Asia here, fifth place, Latin America and the Caribbean, and so on. Okay, so this is net anthropogenic greenhouse gas emissions per capita, so that's per person, and for total population. So North America, it's about, it's the highest per capita. Tons of CO2 equivalent per capita, and you can see, this is in 2019, this is for the year. So North America, it's almost 20 tons per person. The highest, and then you have Australia, Japan, and New Zealand are next, and then Eastern Europe, Middle East. By the time you get down to Africa, it's about 3, 4, and Southern Asia, it's about 2 to 3 tons per person per year. So you can see, there's been now these people are bearing the brunt of a lot of the climate change, and they put in the least. When we talk about population growth, right? Population's growing much faster in these places, but you have to take population times the effect per person, which is much lower on the carbon budget, okay? So it's completely disproportionate, okay? And the time frames are from, it's from 1850 to 2019. And this guy here is just 2019. Okay, this is by region. This is global net anthropogenic greenhouse gas emissions by region, 1990 to 2019. And you can see the proportion. So the total here in 1990, 38 gigatons CO2 equivalent. The total here, 2019, 59 gigatons CO2 equivalent. Shipping is this 2%. And you can go through. So North America's dropped from 18% of the total to 12, only because the other countries have come up, like Eastern Asia, 13%. It's doubled the net anthropogenic greenhouse gas emissions have doubled in Asia, Latin America and the Caribbean about the same, and there's growth in a lot of these other places. But Europe was 16, 13, 10. Europe's dropped. I mean, Europe has done a lot for energy efficiency. And these are some of the regions here. So population in millions of people in 2019 in the different regions. The GDP per capita, you can see, so the richest countries. I mean, look at Australia, Japan, New Zealand, 43 here in Europe. North America, 61, right? The highest GDP per person, the richest countries. Net greenhouse gas production and CO2 from fossil fuels and industry and so on. So this has the breakdown of the different places. And, if you look at the, so you can see things are very disproportionate in the world, very heterogeneous world, not homogeneous. These are the changes of different indicators around the world. So we've got the atmosphere and water cycle, the ocean, the cryosphere, carbon cycle, land climate synthesis, and the confidence, medium confidence to facts. Facts are above virtually certain. And you can see, warming of global mean surface air temperature since 1850 to 1900, fact. The range, 0.9 to 1.2. Okay, well, it's closer to 1.2 right now. Warming of the troposphere is a fact. Human contribution assessment, it's the main driver, meaning very likely. So this is how you read this. Cooling, we've been warming the troposphere, the lower atmosphere. Less heat's going up to the stratosphere, so the stratosphere has been cooling, and that's virtually certain. Humans have been the main driver since 1979 to the mid-90s. Large-scale precipitation and upper troposphere humidity changes have occurred, and there's a bit less certain, but it's likely high confidence, but it's a bit less certain. Expansion of the zonal mean Hadley circulation since the 80s. The assessments being yes in the southern hemisphere here. Okay, so you can look at these things, the ocean heat content going way up, salinity changes, global mean sea level rise, Arctic sea ice loss since 1979. How can this not be a fact? I don't understand. It says very likely. Very likely we've lost Arctic sea ice since 1979. Well, I don't know. That's the fact. Just look at the satellite map. Reduction in springtime snow covers happening since 1950. Greenland ice mass loss, Antarctic ice mass loss, retreat of glaciers. That's not just glaciers in Greenland and Antarctica, it's glaciers in mountains, high elevation regions. Carbon cycle, the amplitude has been increased. If you look at the rise and fall of the carbon each year, you can see that the amplitude is increasing. Acidity of the global surface ocean has been happening. Mean surface air temperature over land is about 40% larger than global mean warming. Well, it's actually higher than that. I think it's about double, triple in some regions. If you go up to high latitudes, it's much higher. Okay, so anyway, that's that's an interesting figure. And then this one here shows how climate change has impacted human and natural systems around the planet, with those who have generally least contributed to climate change are the most vulnerable. So this is heat. This is hot extremes. This is showing an increase. These colors is an increase. Decrease is darker gray, and then lighter gray is limited data. Low agreement is a slash. And then the dots are confidence, high to low. Okay, so hot extremes, most areas of the planet are getting hotter. The acronyms are here. CNA is Central North America and Eastern North America they haven't had so many hot extremes. Southern South America looks like, it hasn't actually, there's not a lot of data there, not a lot of data in Central Africa, but basically, a lot of these most of these are 3 dots, so there's high confidence that there's more heat extremes in most parts of the world, and heavy precipitation. There's an increase in heavy precipitation, Central North America, Eastern North America, Greenland, parts of South America, Southeast South America, lots of Asia, Russia, higher, Western Africa, Southern Africa here, Northern Australia, more rainfall. Other regions, the gray areas are limited data. Okay, agriculture and ecological droughts. We're having more droughts. So we've got them in Western North America. We've got them across Europe. Europe is being hit extremely hard by drought. I've done some videos recently on that. Big chunks of West Africa, same thing. South America, Southern Australia. Okay, there's an interesting here. Northern Australia is actually having a decrease in agriculture and ecological droughts. They're getting some rain in northern Australia. So there you go. Okay, this next figure shows the vulnerability of the population and the per capita emissions per country. So each country is a dot here. The relative average national vulnerability per capita is highest. These are the emissions, so emissions from low to high. So look at all these vulnerable people here. The most vulnerable people are the people with very, very low emissions per capita. As you get higher and higher emissions per capita, as you get, which is coming this way, as you get higher emissions per capita, you get less and less vulnerability. It sort of flattens out here. So yeah, really the, vulnerability differs between and within countries. It's exacerbated by inequality and marginalization. The people that have caused climate change, the countries that have caused it, the brunt of it is going on people that had nothing to do with it, right? So there's huge inequality, basically. So this is some of the observed impacts, related losses and damages. So it's divided by region and globally. So water availability. So here's the key adverse impacts. There's some positive impacts if there's a slash coming through. So physical water availability, some areas are getting more rain, but all of the areas are getting less in all the continents, but there's some regions within that are getting more rain. Crop production, animal and livestock health and productivity, fisheries yield. So things are shifting. Health and well-being, adverse impacts everywhere to infectious diseases, think coronavirus. Heat, malnutrition, and harm from wildfire happening in every region. Mental health suffering in every region, not assessed in Central and South America. Displacement, migration of people. Okay, it's not being recorded in Australasia, but it's happening everywhere else. Cities, settlements, and infrastructure are getting inland flooding and damages, storm-induced damages in coastal areas, damages to infrastructure from wind events, etc. And of course, the economy is suffering in all of these places around the world. And then these areas down here, the climate-driven changes are observed in these ecosystems, but there's no assessment of the impact. Okay, well, it's Logic 101 that says, most of them it's not good. So it's divided into terrestrial, freshwater, and ocean, changes in ecosystem structure, species range shifts, right? Species are on the move, and changes in seasonal timing, which is phenology. Think of when, the flowers come out, then the insects come out to pollinate the flowers, and the, animals, bees or whatever, go to the flowers and spread the pollen. But, if the timing is changing, then whole species can actually perish quickly because they don't have the food when they expect it. Let's move down a bit to this. The responses to date: we've had international climate agreements, rising national ambitions for climate action, along with rising public awareness. It says they're accelerating efforts to address climate change at multiple levels of governance. Mitigation policies have contributed to a decrease in global energy and carbon intensity, with several countries achieving GHG emission reductions for over a decade. That's just a handful of countries. Low emissions technologies are becoming more affordable, with many low or zero emissions options, et cetera, et cetera. This is all sounds great and hunky-dory, but CO2 level, the greenhouse gas levels still are rising at record rates. So we haven't done anything really. It's the bottom line. They say that we've slowed it down maybe, but it's still rising like a bat out of hell. Let's look at the next figure here. This is renewable electricity generation is increasingly price competitive. Some sectors are electrifying. So we've got the market cost this is the cost in 2020 dollars per megawatt hour. Photovoltaics significantly dropped. This is the fossil fuel cost line here. So photovoltaics are now cheaper than fossil fuels. Onshore wind has always been cheaper than fossil fuels, but it's dropped down significantly cheaper now. Offshore wind, a little bit more expensive than onshore, but it's, the trend is, rose here, the trend is down. Lithium ion battery packs, huge decline in cost. This is 2000, 2010, 2020. It's the last couple decades. Market adoption. The installed capacity is increasing, exponentially for all of these different things. So this is all a good thing, but, fossil fuels have still been increasing at much lower percentage rates, but still much more than the total amount of renewable increases is the problem. Okay, so that's a good thing. Let's just go to the next key point here. Gaps. There's gaps between global ambitions and the sum of declared national ambitions. Okay, so mitigating, they're still talking about mitigating. For mitigation, global greenhouse gases emissions in 2020 implied by NDCs would make it likely that warming will exceed 1.5. Of course it's going to exceed 1.5. Just look at the graphs. The next El Nino will bring us over 1.5. And of course, it'll be much harder to limit warming to 2. We've probably lost 2 degrees already. There's systemic barriers such as funding, knowledge, and practice gaps. Lack of climate literacy and data hinders adaptation process. Not enough financing for adaptation. Constraints to climate action, in particular in developing countries. So yeah, these things aren't moving quick enough. We're getting abrupt climate system change, and the society's only reacting, taking small steps comparatively. These are the emission and implementation gaps with projected global emissions in 2030 under the nationally determined contributions, the NDCs. So there's gaps. We have to do more. If there's no way we can hold, there's huge gaps. If we had a hope of limiting warming to 1.5, which we don't, there's huge gaps. 2 degrees. We have to do way better. Like, we're just not. Yeah, I mean, we're failing. This is projected global greenhouse gas emissions from NDCs announced prior to COP26. Would make it likely that warming will exceed 1.5 and also make it harder after 2030 to limit warming to below 2. So basically, if you look at the emissions, greenhouse gas emissions, this is again gigaton CO2 equivalent per year. We're approaching that 60 mark, right? And this is where we are with error bars. We're still heading up, and this is what we have to do. This is a trend from implemented policies. Still more and more warming. This is what we would have to do to limit warming to 2 degrees with 67% chance, or 1.5 with 50% chance after a high overshoot. Right, so now they're talking about, well, we're going to overshoot in the carbon, and then we're going to have to bring it down even faster. Well, yeah, okay. Limit warming to 1.5 with greater than 50%. I mean, we'd have to plummet in emissions. You know, look at these numbers going down to like under 10 gigatons. You know, we'd have to cut back almost from 60, almost 60 where we are to 10. Like, really? You know, we ever going to do that? No. Even 2 degrees? No. So, you know, we're heading, here's where we are right now. Can we bend the curve down? Right, it's not looking too good. We need some miracle sort of cure or something. Understanding net zero CO2 and net zero greenhouse gas emissions. Of course, they're different things because we've got other greenhouse gases that are causing a big percentage increase of the warming. You know, methane, nitrous oxide. Scenarios, global warming levels and risks. I'm not going to talk about that this video. Let's see what this is. So socioeconomic changes influence emissions that change climate, which drives impacts risks. And here's where we are with the different scenarios from AR6. So low emission scenario, high emissions. This is where we are right now. We're almost at 60. And yeah, we're heading to a much warmer world. This is business as usual, which is where we're heading. Okay, so it's all going in the wrong direction, and the risks are going way up. Right? This is the risk. Here we are at 1.1. The risks are already red. You know, if we hit the 2 degrees, anything above, I mean, we're risking losing civilization completely. These are the categories. Limit warming to 1.5, greater than 50% chance, no or limited offshoot. The scenarios, you know, where that would happen. I mean, we're heading here, like we're heading to craziness. So you have these climate impacts drivers creating hazards, and of course, so the risk is the hazards connected with the vulnerability of things is a big factor. The exposure to the hazard is a big factor, and your response, how effective you're responsive. These things all determine the risk, if you like. Future warming will be driven by future emissions. Oh, okay, well, that's interesting. I mean, of course, and will affect all major climate system components, every region experiencing multiple and co-occurring changes. Many climate-related risks are assessed to be higher than in previous assessments. Projected long-term impacts are up to multiple times higher than currently observed, and so on. Compounding, cascading risks across sectors and regions, irreversible changes, and so on. So they talk about future warming. I mean, it's a very dire report, but, you know, so let's have a look. I talked about this figure. This figure, you know, with every increment of global warming, regional changes in mean climate and extremes become more widespread and pronounced. So we've got the world at 1.5, 2, 3, and 4, and you can see, you know, the annual hottest day, the soil moisture, so drought in many regions. I mean, look at Europe. I talked about this in the last video on that was in the shorter form report. Okay, so I'm not going to dwell on it here. I'll just remind you of its existence. Same with this video. Same with this figure about future climate change increasing the severity of impacts across natural and human systems. You know, at the different temperature ranges, and you know, look at the horrendous you know, belts around. How does anybody live near the equator at these sort of temperatures? You know, look how hot it's getting. Heat, humidity risks. So the blue areas, you know, these areas basically uninhabitable because it's too hot, too humid, you can't work outside, you're past wet bulb temperature, that sort of thing. Okay, food production being threatened more and more in different regions, fisheries yield, same sort of thing. So, we're heading to a world of hurt. And I also talked about this figure. These are the burning embers, if you like. It compares AR5 risks to AR6 risks. Things are all going south, pardon the southern hemisphere. That term going south, it means going downhill, but I don't know do they say in the southern hemisphere things are going north to mean that things are going downhill? I don't know. Anyway, I talked about this figure again in my first video. This shows examples of key risks in different regions. So small islands, North America, Europe, right? All the different regions. So some of the things that are happening with the risks at the various temperatures. And we're already at 1.1. Remember, the next El Nino will probably take us to 1.5. You can just figure out, how much the global temperature is rising per decade, and take that range as the upper one and maybe half it, or take, maybe half of it, and that will be the reality, because climate change is accelerating. You can do these back of the envelope sort of things, see where the risks are. With increased warming, of course, adaptation options will become more constrained, less effective. Losses and damages increase. These are very highly nonlinear increases, right? Additional human and natural systems will reach limits of adaptation. Maladaptation can create lock-ins of vulnerability, exposure, and risks. And there you go. It's basically polite ways of saying that we're basically effed. So sea level rise will continue for millennia, but how fast and how much depends on future emissions. Sea level rise greater than 15 meters, that's about 50 feet or so, cannot be ruled out with high emissions. Unavoidable sea level rise causing loss of coastal ecosystems and ecosystem services. Groundwater becomes salty, right, becomes wrecked. Flooding and damages to coastal infrastructure. 1 billion people exposed by 2050. That's about an eighth of the global population. Extreme sea level events that occurred once per century will be 20 to 30 times more frequent. How do we respond to sea level rise? We need long-term planning, ecosystem-based adaptation, sediment-based protection, elevating houses, protect levees, protect barriers, planned relocation, right? So forget about sustainability, think of managed retreat. Okay, that's whenever you hear the word sustainability in your mind, think managed retreat, because that's where we're really at to call it the what's really happening. And then timescales for things to happen. Of course, limiting human-caused global warming requires net zero anthropogenic CO2 emissions. 1.5 and 2 degrees probably gone, but we need rapid, deep, and immediate greenhouse gas emissions reductions in all sectors. Exceeding a warming level and returning, like overshoot, there's increased risk, potential irreversible impacts that maybe make this impossible. Okay, so we're getting there. Remaining carbon budgets to limit warming could soon be exhausted. 1.5, well, again, they're still talking about the 1.5. So they show historical emissions, remaining carbon budgets. So this is in gigatons of CO2, cumulative. So this is, 1,000 gigatons of CO2 up to this point, 2,000 to this point. Here we are in 2020, and this is the budget in, again, gigatons of CO2, 500, so 500. So just take, it's about, this is gigatons of CO2. Is this equivalent? It should say equivalent there if it is. Okay, so, you know, we don't have much. We're basically 1.5 to hold the 2 even with any decent percentage of chance. We need to slash emissions, right? This is basically the 2020, the next, up to 2030, you know, we're going to blow through that 1.5 budget and then blow through the 2 budget shortly after. Every ton of CO2 adds to global warming. So this is historical global warming, and this is the different scenarios. We're on this scenario right now. This is business as usual. SSP 5 to 8.5. This is key characteristics of the model global emissions pathway. So the different C1, C2, the different categories, like C1 is limited warming to 1.5, no or limited offshoot, and basically what we would have to reduce global emissions to in order to achieve these things. So it's detailed. If you want the details, you can go and have a look at it. I'm not going to dwell on that this video. I'm just touching on this. Global modeled pathways that limit warming again to 1.5 really, right? Basically, we needed policies in place years ago. This is greenhouse gases, CO2, methane, right? So we're pushing limits everywhere. Mitigation and adaptation, they talk about. What else do we have? Deep mitigation. So, right, there's more and more talk about overshoot, having an overshoot and then recovering because, well, they got to write something in these reports, right? I wonder when they're going to eventually have one page for this report. Say, yeah, we're aft, we can't do, and then call it a day. This is some pathways again to 1.5. Right, really, okay. I showed you this graph, this illustration in my previous video. So, you know, it's talking about, you know, how do we enable individual and collective actions? You know, we have civil society, the private sector, and governments. And right now, the governments are being controlled by some of the largest companies in the private sector, including fossil fuel companies. So there's basically hijack of democracy. You know, it's not conducive to solving these problems. So there's different pathways and stuff, so that I showed already. This guy here, I don't think this was in the previous report. So exposure to a coastal flooding event that currently occurs on average once every 100 years. So it shows you the number of people that would be affected in the different places. So population exposed in 2020 is the gray person. Additional population exposed in 2040 under a mid scenario, which is SSP 2 to 4.5, shows you the additional people. So, you know, significantly, you know, the small figure is 0.1 million, the large one is 1 million. Okay, so it shows you the increased frequency of extreme sea level events by 2040. You know, lots more on the coastlines all over the world, basically. Example of complex risk, impacts from climate extreme events of cascading effects on food, nutrition, livelihoods, and well-being. So more frequent, more intense extreme heat and drought, you get less soil moisture, so the food yield goes down. You get reduced household income of farmers, reduced labor capacity, right? Food price increases, reduced food security, more malnutrition, decreased quality of life, right? And these things all interact and intertie. You know, we really need to think of these systems things that are going on. I'll just show a few more figures. Okay, I showed this. These are some of the ideas there's multiple opportunities for scaling up climate action talks about different things: solar, wind, reducing methane, bioelectricity, geothermal, etc., etc., etc. Nuclear should have a huge chunk of this, but it doesn't in this scenario. And then demand side, reducing the, not wasting so much food, having more local food, reducing land transport, buildings more efficient, etc. And these are the percentage of possible reductions of everything, with mitigation methods. What is this? Near-term adaptation and mitigation actions have more synergies and trade-offs with sustainable development goals. So you have these different, there's the 17 sustainable development goals. I talked mostly about 6 recently because of the water conference. And then you have a scale here where there's synergies, there's trade-offs, both synergies and trade-offs. And limited evidence, no assessment for the white areas. So you can see with a lot of the sustainable goals, there's connections with the energy systems, with urban and infrastructure, land, ocean ecosystems, society, industry, and there's both mitigation and adaptation things possible. Okay, so they're trying to, make progress on these sustainable development goals, but we're heading backwards, unfortunately, because of climate change. Then they talk about political commitment or lack thereof, and so on. Finance, international cooperation, and technology are critical enablers for accelerated climate action. And let's just go, we're nearing the end here. The feasibility, effectiveness, and benefits of mitigation and adaptation actions are increased when multi-sectoral solutions are undertaken that cut across systems. Yeah, okay. A lot of the stuff is kind of obvious, but the way they say it is, they got to say something in the report. Right. So anyway, so there you have it. So they're getting there. These reports are getting closer and closer to the truth. Basically, finally they're not holding back so much, and it'll be interesting to see when the full volume comes out, how that is different. So now I've talked about the summary for policymakers in my previous video on AR6. I've now talked about the longer report, and I'll talk about this one when it comes out soon. So thanks for listening. Please consider going to my website, paulbeckwith.net, and donating to support my research and videos as I connect the dots on abrupt climate system change. Thanks for now.